Welcome to the final part in the Rumprun unikernel video series Extended Trilogy. This is chapter 4 under the Rumprun unikernel, where we look at what resides under the application layer in the Rumprun unikernel. So essentially we figure out what the whole system ate for lunch, or dinner, or breakfast, or as a snack. So why would you be interested in this? Well, obviously if you want to do your own tweaking and tuning with the Rumprun unikernel, then it's kind of obvious, but even if you just want to run applications, it helps if you know a bit more. You'll be able to run your applications better once you understand how the system functions internally. And it's not really that complicated. There are not that many parts in this system, because the whole point of the system is to keep things as simple as possible, but no simpler than that. And why am I interested in this? Well, I recently finished the chapter on the Rumprun unikernel in the Rumkernel book, and to debug it, I figure out if it has bugs or problems. Use the rubber duck debugging method, where I explain it to a rubber duck, or explain what I wrote to a rubber duck. But since I don't have a rubber duck, you're the rubber duck. So if you want to play the home game, you can also read what I wrote either before or after or during watching this video. So you just go to book.rumkernel.org, and unfortunately I can't tell you where exactly you'll find the chapter, because the site will probably change a bit on May 31st, which is my internally set deadline for finishing the book. But it should be in the ecosystem chapter under Rumprun unikernel, so you can check there. Okay, so let's get started. So it helps always to start with the architecture diagram, which I have drawn and which now magically appears on the screen. So so this is essentially a layer or a representation of the layers in the stack. So first of all, there are two stacks. I'll come to that, or why there are two stacks shortly. But in the middle of each stack you can see the rumkernel, which does things what the rumkernel usually does: provides drivers for the applications which are on top. And we want to run the Rumprun unikernel on various platforms, bare metal, KVM, and so forth. And the rumkernel doesn't run directly on those platforms, so we need our rumkernel runs on some sort of, well, not some sort of, but a sort of abstract representation of a platform, which is defined by the rump user hypercalls. So we need something on top of which we can implement the hypercall interfaces, so that we can actually run the rump kernel and then the applications on top of the rump kernel. So we have the bare metal kernel, which is essentially a very simple operating system, which essentially only does Bootstrap, thread scheduling, page level memory allocation, low-level interrupt handling, and I guess that's it. I can't think of anything else off the top of my head. There's probably some minor thing which it does, but it's really a simple piece of code. So just I forget, 1,000-ish lines of code. So it's pretty easy to check out what it does, and well, maybe it's a bit more than 1,000. But anyway, it's compared to the normal operating system, where you have the non-driver part would be, I don't know, 100,000 lines of code. Well, maybe not that much. Between 10 and 100,000. It's still a huge deal simpler, because we really don't need that extra complexity here. And yeah, so that will soon look at some code examples of what the bare metal kernel does. But yeah, so then we can move on to the top of the stack where you just see applications, and that's where the differences in these stacks really are. So the left side stack is a full POSIX application stack where you can run regular POSIX applications. If you watched the first chapter in this series, you remember we ran MPEG 123, which is a POSIX application. And on the right we have custom applications which don't run on top of POSIX, they run directly on top of rump kernel system calls, and in some cases they call the bare metal kernel directly. The POSIX applications cannot call the bare metal kernel directly because they don't need to, and well, if you really work hard you probably can, because as you know, the Rumprun unikernel doesn't really have any internal protection boundaries, so as long as you can jump from your application code to the right address you can call it, but I mean, it's on purpose made difficult so that you don't do it because you don't need to do it. And this is in line with the principle of minimalism. So you always expose the minimum amount of interfaces that something needs to run, because then you generate the least amount of spaghetti, and then there's the smallest probability for, you know, a butterfly flipping its bits, or well, a butterfly flipping bits somewhere, and 6 months later your code breaks, because that's what happens to spaghetti. So POSIX applications run only on top of POSIX. Custom applications which don't need POSIX, which are a bit lighter weight, which can be optimized more heavily, customized more heavily. Then again, you probably also need to write them or at least port them, so you know it's a trade-off. But anyway, I won't get into more details on that. So yeah, so let's start from the bottom. So like any operating system, this one also needs to be bootstrapped, and well, it's sort of boring code, but let's look at it anyway. So it's of course a platform dependent operation, and we'll look at the hardware platform which is applicable for KVM and bare metal and what have you, and specifically we'll look at the x86 64. So after we enter the bare metal kernel from the bootloader, we jump into start, which is implemented in this assembly file. So here, so essentially this is what every operating system does. So we operate, or we support only multi-boot compatible bootloaders, so that means we're put in 32-bit mode and we have some things set up. The multi-boot provides us with some idea of how much memory we have available and so forth. But essentially we just switch to 64-bit mode, highly commented code. And here's the 64-bit mode, which we enter after we've switched to 64-bit mode, and then we just call x86 boot, which is implemented in C. And now we are capable. Now we're in 64-bit mode and capable of running C. And this bootstrap stuff is actually, I guess, so boring that we'll not waste time going through it. But if you really want to know, you just look at what x86 boot does and then follow it from there. So there's not really much. Set up the console, calculate how much memory we have, initialize the page allocator, set up interrupts. I don't know, that's probably pretty much it. I think I maybe wrote it in the book chapter, but yeah, the C startup code initializes the console and performs various architecture-specific initializations, such as setting up the interrupt controller. Yay. Okay, so let's move on to something more interesting. So scheduling. So if you know rump kernels, you know rump kernel doesn't implement a scheduler so as to make it highly integratable to anything or to everything. And the scheduler is implemented, the BMK scheduler specifically. Oh, well, actually, let's look at the contents of lib first. So we have various libraries in here, and this is the machine-independent core of the bare metal kernel. This is the rump kernel hypercall interface. Then we have some drivers, extra drivers for the rump kernel, and then we have some things which are sort of more toward the application layer of the Rumprun unikernel. So I think we'll only look at this today, and if you want to see what the rest of these 8, feel free to clone this repository and figure out what's in there. So yeah, so the scheduler anyway is implemented in here. As you can see, there's not a lot of code in here. There's a memory allocator, page allocator, scheduler, printf. Now about printf, the rump kernel of course provides us a printf, but since we like to keep things as separate as possible, this has a duplicate printf implementation, which is sometimes duplicating code, especially things like printf which never change, is a better idea than trying to use the same code, because now we have clear distinctions between the abstraction layers as opposed to everything being spaghetti-like. Okay, so anyway, so the scheduler, I don't know if we actually need to look at the code. I guess you can look at the code yourself. Yeah, I'm not gonna start explaining the code, but let's see what I wrote about the scheduler. So with the scheduler, well, the most important thing to know is that it's a cooperative scheduler instead of a preemptive scheduler, which means that you need to, or a thread needs to explicitly state that, okay, now I'm finished running, I'll block, and then the scheduler will schedule something else, as opposed to a preemptive scheduler, which you see in other environments such as regular operating systems, where the operating system decides when the thread will be unscheduled. Now, of course, if the operating system has control of threads or full control of when threads are scheduled and unscheduled, then no single thread can hog the entire system without the operating system agreeing. But on the other hand, scheduling might happen at bad times. An application is just in the middle of some critical section, or holding a lock, holding a resource, and it wants to just finish processing. So in my opinion, preemptive scheduling is weaker than cooperative scheduling, but it's a necessity in some environments. So when I say a thread must explicitly state it wants to unschedule, well, if you're running POSIX applications, then you never really see this or if you're running POSIX applications on the Rumprun unikernel, you never see this in practice. Or let's say you never need to actually explicitly call, or your application never needs to state that it explicitly needs to state that it needs to unschedule, because what happens is that when your application makes a system call into the rump kernel, and through the drivers in the rump kernel it bounces around, and then it decides to block somewhere. It goes to the rump kernel hypercall interface, and and there the rump kernel hypercall interface, the rump kernel hypercall implementation, I mean libbmk underscore rump user, then knows that okay, now we have to block, and it calls the bmk scheduler, which then does the right thing. Yeah, it's probably easiest to explain that with a code example, which I actually also did in the book, but let's just duplicate that here. So let's write a small piece of code which just essentially sleeps forever, like this. Good. We compile it, we bake it. I mean, this all should be pretty familiar to you from the, was it the second chapter in this extended trilogy? I don't know if that's the middle chapter, but anyway, so if you don't know what I'm doing, check out that chapter. If you know what I'm doing, then hang on. Okay, we bake it. Let's run it with the debugging support. Okay, so now it's essentially running. I'll just move this window out of the way because it's not that interesting. And then let's attach a debugger to it. Let's put a breakpoint to sleep and attach the debugger. Okay, and continue. Okay, now we're in the application. So well, I forgot to compile the application with debugging symbols, but essentially this is the main of the application and it's just called sleep. Now if we put a breakpoint into schedule, I happen to know that schedule is where the scheduler does scheduling, partially because I wrote the scheduler, but you can just trust me on this. So if I put a breakpoint there and continue executing, the next time, or when we hit the breakpoint, should be, or is, well, hopefully is, otherwise there's a demo effect, is when the currently running thread, which is our application thread, has voluntarily decided to give up the CPU because essentially it wants to sleep for a second. Continue, hit the breakpoint, and now the backtrace is a bit longer. So we can see that schedule is inside the scheduler. Sched block has been called. Sched block has been called from rump user clock sleep, which is in the rump user or the rump kernel hypercall implementation, which is implemented here. And essentially the rest of this is just going through the rump kernel, the system calls, and essentially going through libc to even reach the system call. So that's essentially what can happen, or what happens every time a POSIX application makes a blocking system call, and this happens completely transparently. So there's the only difference to the application is if you have a thread in your application which never makes a blocking system call, then you run into problems, because essentially that thread will run forever and no other threads will run, and things will fail because the rump kernel threads don't run, no other threads run. So something you need to be aware of. You can manually insert, if you have such an application, you definitely want to run it on the Rumprun unikernel, then you can insert sched yield calls into the application, but that's pretty much the only way you can run those sort of applications, or that's an easy way. You can of course radically restructure them, but that's probably harder. Yeah, so I guess that's whatever, or what I want to discuss about the scheduler. Then the hypercalls, well, like I think I already mentioned, the hypercalls are implemented in this library, and as you can see, it's this is not a lot of code, essentially, especially since you know, the first half of each file is the copyright, so this is just a handful of lines of code. Very simple. You can study this if you want. I won't go into details on what this has specifically, or what the implementation of this is like, but yeah, it's quite simple. Oh yeah, one thing I probably should mention also pertaining to the scheduler is libpthread. So libpthread communicate, or essentially libpthread, the NetBSD implementation, it's implemented on top of the kernel lightweight processors provided by the NetBSD kernel. And since the rump kernel doesn't do threading, it doesn't implement the necessary system calls for, or it doesn't implement the lightweight process system calls. So in order to use the NetBSD pthread library, we have an implementation of those system calls here in this file, and essentially they just tie up these calls to the BMK scheduler. So as you'd expect, it's just an adaptation layer. There's one problem with this current implementation, is that it's implemented as a libc symbol, not really as a rump kernel system call, and that can cause some havoc if you want to run or build your Rumprun unikernels without libc support at all. If you don't know that you'd want to do that, then you don't have to worry about it, and if you do know you want to do that, then you probably also know why this is a problem, so I won't really get into that in more detail. Then what else? Well, actually the rest of the chapter that I have written is talks about the tool chain and the baking and things like that, but I think we already covered those things, or all of those things, in earlier establishments of this Rumprun unikernel extended video trilogy. So I won't have to do that here. So yeah, I guess that's it. Anyone have any questions? No? Good. Well, thank you for watching. Have a nice day, and go to book.rumpkernel.org to read the book. Like, you've now watched the movies, but of course, as usual, the book is much better.